Hi, Mr. Wong.
Hey, Mr. Wong. We're Stefan L and
Costner M.
and we're doing our own version of a problem from the Chapter 4 Version 1 test.
In Calculus 12.
Exactly. We changed a few of the numbers on it, and it's the very last question on the test. Sketch the function f of x equals x cubed minus 3x plus 3 on the interval minus 2, minus 2.5, 2, where negative 2.5 is a closed interval and 2 is an open interval, and compute the critical points, the inflection points, the intervals of increase and decrease, the concavity, whether it's up or down, absolute and local minimum and or local minimums and or maximums, and the intercepts, all of this analytically.
We're going to start by computing the endpoints. Endpoints. As you see, our domain is negative 2.5 and 2. So we're going to start by putting 2.5 into the f of x equation. F of negative 2.5. Negative 2.5 cubed minus 3, negative 2.5 plus 3. That's going to equal negative 5.125.
And we're going to put that on our graph. Negative 2.5 and negative 5.125 is colored around there.
Awesome. Now we're going to do the other. Now we're going to do the other point. F of 2. This is the right end point. Notice it's an open interval. Same of our f of x equation. 2 cubed minus 3 times 2 plus 3. That equals 5.
2, 5 is somewhere on right there.
Open interval.
Open interval, my bad. There you go. So there's discontinuity there. Next we're gonna find the x-intercepts and the y, all the intercepts. So x-intercept, we're gonna set f of x is equal to 0. X, which equals x cubed minus 3x plus 3. And then it's about, using estimation, it's about 2.1. So we have an x-intercept at x equals 2.1. And for the y-intercept, we're going to say that f of 0 is equal to about 3. There's our y-intercept.
The next step is we find the critical points. To find the critical points, we have to find the derivative of the function. This is just simple differentiation. Difficult?
No.
No. Alright, we're going to see a simple differentiation here. 3x squared minus 3. The critical points occur when the derivative equals 0. F prime of x equals 0. F prime of x equals 3x squared minus 3. The easiest way to do this is to factor out a 3. And you're left with the difference of squares. X plus 1. Straight out of grade 10. Awesome. So from this we can gather that there is x equals 0, so the function equals 0, at x equals 1 and negative 1. So we know those are the critical points. Now we have to determine if they are minimum or maximum. So, and we have to determine if the intervals in which it increases and decreases using these points. So what we're going to do is we're going to find points around 1 and negative 1 to test with. Let's start with 2. This is also known as the first derivative test.
Right here he's just subbing 2 into the function. Pretty simple stuff.
This equals 9. 9 is greater than 0. Therefore, we have a increase at this point. Next we're going to test with f prime of 0. And that equals -3. That is less than 0. Therefore we have a decrease. Next we're going to test with f prime of -2. That also equals 9. 9 is greater than 0. That increases. Alright.
So, we're going to draw these lines. We're going to draw these lines, we're going to put, the intervals are between negative, Costner's going to write up just where the intervals are. I'm going to draw them on the graph. At -1 and 1, the graphs behave in different ways, or the graph behaves in different ways. So it increases from -infinity to -1. So it increases right here. And it also increases from 1 to infinity. It increases right here, from the orange line to the right. Which means that in between the two, it decreases between -1 and 1. There you go.
Perfect.
Next,
so we know that because it is increasing on these two intervals and decreasing on this interval, that this point is
the point of 0, 1.
Point of 0, 1.
1, 0, sorry.
1, 0. That would be a maximum?
No, that'd be a minimum.
That would be a minimum.
Because it goes from decrease to increase. So it's decreasing here, and then it begins increasing.
Absolutely, increase. There we go. And this one here would be a maximum.
Exactly. It goes from increasing to decreasing. So, next we're going to find what those minimums and maximums are. Just get some space here.
You have to do solid contents.
So at those points, f of -1, we just sub it back into our original function. F of -1 equals -1 to the third minus 3, 1 plus 3, and this equals 5, which means we have a local maximum at -1, 5. We're going to solve the other one, the other orange line, this one right here. F of 1 equals, just put it back in, and that's equal to 1, which means that -1, 1, sorry, at 1, 1 is our local minimum. Gonna have, so -1, 5, -1, 5 is our local maximum, and at 1, 1 is our local minimum.
Your concavity?
Yep. Next we're going to figure out where our concavity is. So this is going to be using our second derivative test. So our first derivative is f prime of x, 3x squared minus 3. With some simple differentiation, we can find out that derivative. We had a mistake in the earlier video. I accidentally wrote that the x-intercept is at 2.1 when it's actually at -2.1. So there you go. I just let it clear up. Now we're going to be finding the concavity, whether it's up and down, or at what points it is up and down. Which we have to find the second derivative for that. So our first derivative, which we already found, is 3x squared minus 3. With some simple differentiation, we know that 3x squared, the derivative of 3x squared is 6x, and the derivative of a constant is just 0. And then we test at the critical point. So at the CPs, f prime of 1, as we established our critical points to be 1 and -1. At f side, f of 1, 6, 1 is 6, which is greater than 0. So concavity up, And at f prime of -1, it's -6, which is less than 0, therefore concavity down.
Okay, with that in mind, we need to now find out where the inflection point is going to be. So, back again on that second derivative. The inflection point occurs where the second derivative equals 0. Obviously, the x equals 0, or the graph equals 0 when x equals 0. We know the inflection point occurs when x equals 0. We're going to plug it back into the original equation to find out the y-coordinate. F of 0 equals 3. So the inflection point is going to be right here.
Awesome. At our y-intercept. So there's our line of concavity. There you go. It's just down the. That's supposed to be down the y-axis. So from this, it looks like we have all the information we need to draw our function.
This is concavity up and that's concavity down.
Exactly. So on this, on this side is concavity up.
Down.
Sorry, and this side is concavity down. On this side is concavity up. From this, we have more than enough, or just enough information to sketch sketch our function. So, following the dots and the rules, we got up to our x-intercept, up to our local max, where the function starts decreasing, as it says here, through our inflection point, and as we remember, that was also our y-intercept, down to our local min, and then starts increasing again. There you go. And, oh, no, is that right? Goes up to our open interval. Thank you very much.
That's it for this lesson.
See you next time.